Welcome to my talk on active reversing. My name is Gary Hoglund. I work for a company called HB Gary. We do a lot of reverse engineering at HB Gary. We've been doing reverse engineering for a lot of years, and so this talk is about a methodology that I've been working on for quite a while. The idea is to reduce the cost of reverse engineering. Traditional methods for reverse engineering are very code-centric. A lot of static disassembly, hunting around an IDAPRO, for example. Now, that's a very powerful method, and it works to solve most reverse engineering problems. But the problem with it is that it takes a very esoteric skill set to use IDA to disassemble code manually in your head, create pseudocode. There's many reverse engineering problems that can be solved without going to disassembly. And so I'm going to show you some methods and some tools that I've developed. Some of the stuff is actually in shipping product that you can buy from HB Gary. Other stuff is prototype stuff that I've been working on recently that we're trying to get into the product at some point. So let me go ahead and go through the slides and present this methodology to you. So the goal is very simple. We want to solve reverse engineering problems as quickly as possible and minimize the reliance on reading disassembled code. Now, how is this going to work? The basic premise of active reversing is that the software is already going to reverse engineer itself. It does it as it runs anyways. It has to. That's how it works. So what we're going to try to do is come up with the right strategies to observe the software in operation and learn what we can from what the software is already telling us about what it's doing. So for example, when you perform a user-based action with the software, it makes sense that the software is going to execute some code that relates to something you just did with it. Well, if you could capture that set of code and put it in a graph, you now know that this little cluster of functions deals with the print dialog box or whatever it is that you just did. Code, data, and behavior all interrelate to one another at the same time in the context of the CPU. And because of that, we can collect and tie together those three factors of a program's behavior. So, active reversing is great. It excels at classifying software by behavior. And the other nice thing about it is you only have to be able to use the software. You don't necessarily have to be able to pick apart code. So by using the software and getting it to reverse engineer makes active reversing a very simple process. The business case here, and this is the ultimate reason I'm giving you this presentation, is that we want to save time, and time is money. The problem with traditional methods of reverse engineering, static disassembly, taking apart stuff in your head, there aren't very many people in your organization who can do that very well. They are there. There's probably some of you in the audience who are pretty darn good at it. But the thing is you're not the common. You're the very unique, and you're very expensive, and you can't keep up with the amount of workflow. So the managers in the room are thinking, I have this very small team of guys. I can put them in a room and throw some pizzas and sandwiches at them for 6 months, and they can come out with something. But when I'm an incident responder, and I have exactly 3 days to figure out what this malware is doing, and I don't have a bunch of guys like that, I have a big problem on my hands. So then I don't really use reverse engineering, my most powerful tool, to solve the problems that are facing me today. So by minimizing the reliance on disassembled code, we increase the potential labor pool in your organization. If you're smart enough to read a packet sniffer, you're smart enough to do this. Basically, the idea is if you can take a data structure apart, which is all that a packet is, just a data structure, then you're smart enough to do reverse engineering. The only thing that's in your way, perhaps, is just learning the 30 most popular Intel instructions and trying to keep those in your head. I mean, it's ridiculous. I can't even do it. I have an Intel desk reference there. I'm always looking up, what does that darn instruction do? So for those of you that really do rely on the old school methods of taking apart code, obviously, eventually, you'll be taking apart code at some point. If you have to, for example, reverse engineer an encryption algorithm or a parser, the chances are you will have to read disassembled code. But for the traditional methods, active reversing can take you to the function of interest just like that. You don't have to hunt around and try to figure out the behavior statically. You learn where the locations of the functions are dynamically. Now, another problem with static analysis is that it doesn't actually show you any data, really. It has some data, but the thing is, software is very complicated, and data, for the most part, drives the execution of the control flow. And that data state is calculated at runtime, and it's very complex. There's a lot of intermoving parts. To figure out what it's going to do statically in your mind is nearly impossible. So what you want to do is observe the software. Because it's so complicated, it gives rise to all kinds of emergent behaviors that you can't predict. If you could predict all the emergent behaviors of software, we wouldn't even be here today at BlackHat. And because of this, this is the reason that debuggers are still used, and we fall upon debuggers a lot when we're reverse engineering. When I'm in a debugger, I feel a lot more comfortable because I can see the data in operation. So our reverse engineering method, and I'm going to show you, is very data flow centric. Some of the underlying code is very complicated. We spent over 2 years developing some of the data flow analysis tools that are under the hood that you're not even going to see today. So know that this is non-trivial. But the ability to trace where a particular piece of data goes and how it's arithmetically modified in memory, that is probably over $500,000 in investment. So I'm going to prototype several things and show those to you. And some of the stuff, as I said, is in the current shipping product. If you want to see demos of any of this stuff at your place of business, after the talk, just bring me your business card and I'll make a note. And we'll try to arrange to do either a WebEx demo or something like that at your company or organization. So with that, let me jump right into the methodology. Okay. The methodology goes like this. First, we're going to harvest code and data flow information. The methods and tools we will use to harvest that information will take a lot of different forms. That information will be collected into sets. So we're going to rely upon set arithmetic and set operations for some of our filtering that we'll do later. Those sets are combined into layers, one on top of the other. And I'll show you a screenshot of that in just a moment. Those are smashed down onto a graph. The graph is what we're going to interact with. We call that the working canvas. We will have a graph of information and relationships between objects on that graph. Those are the edges. And that will be refined iteratively until it reduces itself to the answer to the reverse engineering question that we're asking, whatever that may be. Now, you're wondering if a graph is good enough for this. Think about a graph for a second. It's just nodes and edges. We can put any kind of information we want on a graph. So it's super flexible. It could be a data instance. It could be code. It could be just the presence of a particular piece of information in time. Anything you want can be represented by a node. And the edges are just relationships then between arbitrary objects. So a graph can work. In order for it to work, though, it has to be able to illustrate the answer to the question you asked. Now, graphs have been used in reverse engineering in the past. But the problem with graphs with reverse engineering is that they get very large. And when they're large, they're not interactive. And interactive is the key word. If you can't interact with it, it's not very useful. I have a couple of screenshots of some graphs you may have seen before. This is Walrus. This is used for very large graphs. It's a directed graph using hyperbolic graphing. You can grab this thing in 3 space, rotate it around. It's really pretty, but there's absolutely no information I can grab from this because there's too much on the screen at once. So it's pretty, but it's dumb. This is ugly, and it's dumb. Can you actually derive anything of use out of this graph? This is IdaPro, and I know that IdaPro has been working on their new features, have better graphing. This is one of the older methods, but still too much information and not a very good layout algorithm. It's not helping me. Now, I do have a slide here for hyperbolic graphing. That was what the Walrus was. I have code that does hyperbolic graphing, but what I'm starting to notice is with active reversing, my data sets aren't really large enough to warrant going to such an extreme. So what we're going to do instead is take away the idea of hyperbolic graphing. I'll just put it on the back shelf and say that it might have some use someday, but we're not using it now. We're going to use a two-dimensional top-down graph with colors on nodes. It's very simple. Here's a screenshot, and you can see in the corner a little control that's used to manage that graph. So the graph will have color and annotations, and we can put any data we want inside of the nodes, such as disassembly or labels. Now, we'll have on the screen, hopefully, only what matters to our reverse engineering problem. At first, when we get started, we may have a whole lot of information that we don't need. So there's a filtering and refinement process that needs to take place. But we're going to take these iterative steps and filter down to essentially a set of data that only matters to the reverse engineering problem at hand. So the idea of the methodology is we can converge the data set upon the solution. Here's a screenshot of one of the prototype tools I've developed. We see the working canvas on top, and on the bottom is the layer control, and I'll show you a demo of this shortly. The data is being placed into the graph. The data represents control flow that's been exercised at runtime. And off to the right-hand side are various data collection tools that we've been developing. Those can take many different forms. Here's the layer control up close. My inspiration for the layer control is our old friend Photoshop. How many here have used Photoshop before? All right, so you've seen the layer control in Photoshop. It's pretty cool. Multiple bitmaps can be combined together using all kinds of blending modes, light and darken, and they can just be smashed down onto the canvas. So we're not dealing with bitmaps, we're dealing with sets. But the idea is the same. We have sets on the left here, of various control flows that were executed, and we have a blending mode. We have the ability to toggle the sets on and off in visibility in the graph, and we have the ability to change the blending mode, which can represent every possible Boolean operation between sets. Union, intersection, all of it. And then, finally, we can also do things. You can see on the right-hand side of the control I'm talking about here, there's actually little arrows. You can actually nudge the layers down, up, and it even has a flatten all, where it'll smash everything that's visible down onto the working canvas. So it's very similar. In fact, I just basically ripped it off from Photoshop. So set operations are a really easy way to combine and filter your data. If you have, for example, all the mouse operations, and then you did something that you had to use the mouse to do, and that went into a new set, you could subtract out the mouse operations from it, and you're left with only the stuff that was handling the action in question, and it's not polluted, if you will, by the set of all the mouse handling routines. Okay. So here are some of the things that we can harvest into a set. Data flow, like for example, every location that a piece of data is instanced in memory. Every location a class is instanced in memory. We can also show on there a number of times a particular location was referenced, that is execution or data reference, hit counts. The number of functions, or the functions that were covered, we saw that in a screenshot just a few slides back. References to strings, and of course symbolic information if we have it available, such as symbols available in PDB files. So there's the methodology. We harvest, we combine all that stuff together, and we refine the data set down until we get to our answer. That's the high-level 30,000-foot view. All right, how are we going to get started? First step is execution partitioning. What we want to do is take all the functions and try to separate them out into different behavior classes. For example, like I was saying, all the mouse movement goes over here, all the print dialog stuff goes over there, all the print or the packet parsing goes here, general packet parsing goes over there, and parsing the individual protocol headers goes over there. Okay, great. We separate all this stuff out. Let me show you how that's done. Every time you perform an action with the software, it makes sense that the reaction of the software is to produce or execute code related to that behavior. It doesn't have to, but that's just the way that we build software. We write specific parsers in code, and the compiler makes them off into their own functions, and those are the things that are going to execute when that particular packet type comes in. And so naturally, it lends itself to a directed graph. We're going to drop all that on the screen. So let's go ahead and run through some different scenarios. If we send a packet, let's collect all that into a group by itself. Let's send a specific command, something that you can send via the packet, and branch off that and see all the code that handles maybe a file copy operation, or exfiltrating a keystroke log, or whatever the malware is doing. Clicking a menu button on the menu is going to exercise some outer loop message processing, but it's also going to execute whatever code is underneath that menu function, whatever it happens to do, and that's what you can isolate out. Another example is I can have it running, and I can have World of Warcraft running, and I can move my character to the left. And that movement is going to show up as its own control flow. That is the movement handling functions in the wow.exe. And another interesting thing you can do is just unplug and insert hardware. And that'll also cause certain things to happen as a response to a particular plug-and-play event. So there's all kinds of creative things you can start doing. Let's talk about some of those. The first step is just doing some basic things. Rapidly locate functions for a particular behavior. Now, we're going to do that incrementally. How we do that is we first collect noise